This video is going to introduce mixture problems. Here's an example of a mixture problem. The CDC recommends hand sanitizer that's at least 60% alcohol to deactivate the virus that causes COVID-19, but stores are out of stock due to overpurchasing. You have a 32 fluid ounce bottle of 91% isopropyl alcohol at home. It's a good thing you bought this years ago, but since its strength is more than enough, you don't want to waste it. How much lotion with no alcohol in it should you mix in to create a homemade hand sanitizer that's 60% alcohol? Before answering that question, we're going to dig into a couple exploratory ideas. I'd like you to answer the following interactive question. Now, I have a cup with 8 liters of fluid, or 8 liters of liquid. If 50% of the liquid in the cup is acid, then how many liters of acid are in the cup? So 8 liters of liquid and 50% of it is acid, then the number of liters of acid should be 4 liters of acid. Notice how 8 times 0.50 equals 4. This is an example of the concentration equation at work, namely amount solution times concentration equals amount acid. This cup I'm talking about is a container, and you should have your own expectation to use this concentration equation on every container you see. If you ever forget the formula, you can always recreate it by making your own small example, and it's most convenient to think about 50% as a concentration like we're doing here. I just dumped out the container, this first cup. In this cup, there are red M&Ms and blue M&Ms. Each red M&M represents a liter of acid, and each blue M&M represents a liter of water. Note that both acid and water are considered liquids. They're just different liquids. Does this look like 50% of the cup is acid? You look at the color here and you see roughly 50% red. Now I have a second cup. This is cup number 2. Cup 2 contains 12 liters of liquid total. So in other words, I've got 12 M&Ms in here. If 75% of the liquid in this cup is acid, then how many liters of acid are in cup 2? It should be 9 liters of acid in this cup. Notice we have here 12 times 0.75 equals 9, which is another example of the concentration equation, amount solution times concentration equals amount acid. Here's the contents of cup 2. Hopefully it's visible here that there are 12 total M&Ms, and that of these 12 total, 9 of them are red. 9 of them represent acid, 9 liters of acid. Does this look like, even looking beyond just all the numbers, does this at least roughly look like 75% of the container's acid, or that it was 75% red, 3/4 red? All along, I've had this empty bucket. I'm going to turn this bucket around, take the contents of cup 1, put it in the bucket, take the contents of cup 2, and put it in the bucket. Now, what percentage of this bucket is acid? Should we add 50% and 75% from earlier? Well, that would result in a percentage that exceeds 100%. Could you compute the concentration if you knew the amount solution and the amount acid in this bucket? Note that the amount solution in this bucket is 8 plus 12 equals 20 liters, and the amount acid in this bucket is 4 plus 9 equals 13 liters. Plugging in 20 and 13 into the concentration equation for this container and solving for the concentration, we see that the concentration of the bucket is 13 divided by 20, in other words, 0.65. Notice that 65% is somewhere between 50% and 75%, though not exactly halfway in the middle. Halfway in the middle would have been 62.5%. So this somewhere in between kind of thing with the percentage happens in general. Do you see 13 red M&Ms? The 13 red M&Ms, of course, came from the 4 red M&Ms from one cup and 9 red M&Ms from another cup, and 7 blue M&Ms. 7 blue M&Ms because there were 4 blue M&Ms from the first cup and 3 blue M&Ms from the second cup. So the 13 red M&Ms here and the 7 blue M&Ms for a total of 20 M&Ms. Does this look like 65% acid to you? Does this look like roughly 65% of what you see here is red? Just resetting the story here, it's important to point out that the amount of solution in cup 1 plus the amount of solution in cup 2 is the amount of solution in the bucket, right? In other words, the total number of M&Ms here plus the total number of M&Ms here will eventually be the total number of M&Ms in this currently empty bucket. Similarly, the amount of acid in cup 1, just the red M&Ms, plus the amount of acid in cup 2, just the red M&Ms here, will end up being the amount of acid in the bucket. However, the percentages do not add up. So let's draw a diagram here. And in this picture, the red pebbles, these little red dots represent the 4 M&Ms, which represent the 4 liters of acid. And then the 4 blue dots in cup 1 represent the 4 liters that are not acid, or the liters that were water. In the second cup, you see those 9 red dots. Those represent the 9 liters of acid in the second cup. And then the 3 blue dots in the second cup represent the 3 liters of water. It's not going to be typical that we want to draw all of these dots all the time. So what we'll typically do is just, instead of drawing pictures, and we might not even have whole numbers, let's just put an 8 there. We were given that 8 in the beginning. We were given 50%, which we wrote as 0.50. And we had computed that there should be 4 liters of acid in the first cup. So that's represented by the 4 dots, for the 4 red dots, excuse me. In the second cup, we were told this information that there were 12 total liters of liquid. We were told that the concentration was 75% acid, so we wrote that as a 0.75 here in decimal form. And here again, we can apply that equation, amount solution times concentration, so 12 times 0.75, that leads to this 9 here. And so that number 9, the number 9 that we discovered, is what corresponds to the 9 red dots that we see. Finally, we took the contents of the first cup and we dumped it into the bucket. We took the contents of the second cup and we dumped it into the bucket as well. Now, this is so what happens with this is then the amount solution here, it is 8 plus 12, right? How much total liquid should be in the bucket? It should be the yeah, we could have simplified this to 20, but for now, I think it's actually much nicer to just write 8 plus 12. Then we didn't actually have the concentration next. That was the last thing we got. The amount acid, same deal here. The amount acid, it should be 4 plus 9. And I could have written 13 here, but I, for now, just wanted to write 4 plus 9. To clear up that 4 came from those 4 red dots from over here, and then the 9 came from these red dots. So this is a complex problem as it deals with 9 quantities. There are 3 quantities over here, there are 3 quantities over there, and then once we fill in this 0.65, there are 3 quantities here as well. So a total of 9 quantities. And the more complex the problem is, you have to take more things into account. It's very common for students looking at these problems at first to not account for all 9 quantities. In this case, we had to keep track of color. This complex problem couldn't have been done if we ignored color. Yeah, we definitely needed to know the total number of M&Ms in cup 1 and the total number of M&Ms in cup 2, but we also needed to sort things out by color. And with this complex problem, we had to do that. In this case, the color represented, well, red represented acid and blue represented water. It was all liquid, whether it was acid type liquid or water type liquid, it was all liquid, but we had to keep track of things in their sort of constituent parts as well. And that's, I hope, what this picture helps represent a little bit better. Just to wrap up ideas here, generally speaking, most mixture problems, you can actually rephrase it this way. As even if it's not worded like this originally, you can usually think of it as the contents of one cup and then the contents of a second cup, and that you dump both of those containers into an empty bucket. That you can usually think of these problems that way. And as you do so, you should keep track of this idea that you're going to have to apply the concentration equation to each container. That is, you're going to have to do this amount solution times concentration equals acid to each of the three containers, which means you need to keep track of amount solution and concentration and amount acid for the first container. You need to keep track of amount solution and concentration and amount acid for the second container. And you need to keep track of the amount solution and the concentration and the amount acid for the third container. You got to keep track of all 9 of those quantities. Then it's important to keep in mind, as you're keeping track of the 9 quantities, that you'll apply the concentration equation to the 3 numbers that are part of the first container. You'll apply the concentration equation to the 3 quantities that are shown in the second container. You'll apply the concentration equation again here to the final bucket. The amount of solution from this cup and the amount of solution from that cup will total together and add to be the amount of solution in the bucket. Also, the amount of acid in the first cup added to the amount of acid in the second cup. So these two things will add together and they will represent the amount of acid in the final cup. However, the thing that doesn't happen, you'll notice, is that if you add 0.50 and 0.75, that is not going to be the concentration. That just doesn't work out. In the end, for these problems, the amount of acid for the final bucket is going to be actually found 2 different ways. First, you can get the amount acid for the final bucket by taking this number and this number, the amount of acid from the 2 ingredient cups, and adding together. Second, and it depends on how that information is given to you, but one way or another, you're going to end up applying the concentration equation. That is, you're going to take, in this case, the number 20, multiply by the number 0.65, and again get the number 13. So the amount of acid for the bucket is going to be obtained 2 different looking ways. Now they are different looking, but they actually represent the same number. So in these sorts of problems in general, not in this exploration, but in these sorts of mixture problems that you're going to get, you're going to equate the 2 different looking ways of getting the amount of acid. They look different, but they do represent the same quantity.